Hello class, now I'm going to solve question 6 which we hadn't enough time to solve during the tutorial session today. So let's see what this question is about. It says we have a hot surface at 100 degree and it is cooled by attaching 3 centimeter long and 0.25 centimeter diameter aluminum pin fins with this thermal conductivity. So there's a surface with 100 degree uh, at 100 degrees temperature, and we are going to cool it down by attaching 3 centimeter long pin fins, and diameter of each pin fin is going to be 0.5 centimeters. So we are going to have a lot of pin fins over that surface with a center to center distance of 0.6 centimeter. So I'm going to use this 0.6 centimeter from center to center to find out how many fins I can have over that surface. The temperature of the surrounding medium is 30 degrees. So T infinity is 30 degree and heat transfer coefficient of the surface is 35. So H is 35 watt per meter square Kelvin, and it asks us to find heat transfer rates for the surface of 1 meter by 1 meter and find the overall effectiveness of the fin. Okay, great. The first step is identifying the geometry and find out what is happening. So let me draw our base. This is our base. I'm drawing 2D case. So it is going to have, for example, one here, another here, another here, and further more. Okay, now you can see this is our base with a few fins inside. Now I'm going to draw the dimensions we have. So the first one is, if I could change the okay, I can change the color. So let's go. This is going to be okay, it's working. This is my diameter and it is given equal 0.025 centimeter. Then the lengths of fins are given. This is the length, 3 centimeter, and center to center of fins also given, which they are going to help me to find the number of fins. So if I draw 3D case, it is going to be something like this. Over a surface and a lot more fins in both directions, left and right, and bottom, top and bottom. Okay, so this is a pin fin. Now let's check the formulas we have. So I'm going to go back to lecture notes and open the sections we had 4 formulas. So okay, this is the table for efficiency of fins, because you know for heat transfer rate you need to first have the efficiency of the fin. So this is not the this is a straight fin, so I'm not using that one. Our fin is straight pin fin, which is this one, with diameter and length is given. So this is the formula I'm going to use. Fin efficiency is going to be tangent hyperbolic times length corrected length divided by m corrected length, and m is this formula 4h divided by k d, or you can simply use the original formula we had for m, which was hp divided by k ac, and this is the corrected length and fin area, which is the surrounding or convective area. Okay, let's go back and solve it. So I'm going to find m. M is going to be equal hp divided by k ac, or the other formula was in the table, which you can get that formula even here. So if I put the perimeter or circumference and pi, this is the cross-sectional area, I'm going to get 4h divided by kd. So let's go back and check 4h divided by kd. So same formula, they just did the calculation for us. So let's plug in the numbers. 4 times h was 35 divided by k is 237 times 0.0025 meter, which is going to be 15.37 meter power minus 1. So we found m. And then efficiency formula. Efficiency formula for fin is going to be tangent hyperbolic MLC divided by MLC. Let me show you the formula again. This is the formula. Okay, so let's find the, we already find the value, we just need to find tangent hyperbolic m, which is 15.37 multiply by LC, which was 0.03 plus diameter 0.0025 divided by 4, 15.37, again that one. Which is going to be 0.935. Basically, the efficiency of fin is 93%. Now I need to find what is the, how many fins I have, because in the formula, let me go back to the summary page. In the formula, I need fin efficiency, I just found it. I know the fin area, TB, T infinity, H is all given. The only unknown is the number of fins, because if I have the number of fins, I can multiply the number of fins here to get total number of fins. So let's see how I can find the number of fins. The number of fins is going to be this is the total surface, 1 meter by 1 meter, and the center to center was 0.6 centimeter. So I converted to the meter, and I want to find how many 0.6 centimeter I have in 1 meter by 1 meter of my surface. So this is going to give us 27,777 pin fins. Now let's find total area for fin. So area for all fins is going to be the number of fins. Let's put a T here, total number of fins. Area of one fin. So total number of fins was 227,777 multiply pi dl, so surrounding of the fin, so the area here plus area at the top. So area at the top is going to be pi d squared divided by 4. So if I plug the numbers, 27777 pi, diameter is 0.0025, the length was 0.03 plus pi times 0.0025 squared divided by 4. You may say the area at the tip of the fin is not that much. It's very small because diameter is very small. It's like a 2 millimeter. But because we have almost 30,000 fins, that is why I want to include it to increase my accuracy. So the total surface of the all fins is going to be 6.68 meter square. Now I found the total surface of the fins. Let me check the formula again. I also need surface for the unfinned area, or the surface between fins. Let's go back. If I want to calculate area of unfinned surface, it is going to be, because the surface is 1 by 1, so 1 minus 27,777 area of pi d squared divided by 4 of one fin. So basically, if I draw this, it is going to be, these are my fins. I'm looking for the area here. So that is why I calculated area of one fin, which is this one, multiplied with the numbers and subtracted from the total 1 by 1 meter surface. So I get the area between, and it is going to be 0.86 meters square unfinned area. Okay, now the preparations are finished. Now I need to find heat transfer rate for the finned area. So this part is easy. Q dot for finned area is going to be efficiency of one fin and convective coefficient, area of all fins, total area of fins, and base temperature minus T infinity. And this is going to be 0.935 times 35 times 6.68 for the area, and base temperature is 100, infinity was 30, and it is going to give us 5,300 watt. So this is the heat transfer rate for the fin. Now heat transfer rate, because we are going to have heat transfer because of fins and because of the heat transfer area between fins. They're also involved in the cooling of the surface. So heat transfer rate for unfinned area is going to be H area unfinned, TB minus T infinity, because the area between fin temperature is TB. And let's plug it. 35, area was 0.86, and 100 minus 30, which is going to be 2,107 watt. So total heat transfer rate for the heat sink or finned area and unfinned area is going to be summation of those previous. Finned plus Q dot for unfinned, which is going to be 17.4 kilowatt. Now, this is the first part. I found the heat transfer rate for this arrangement. Let me check the question. Says determine the rate of heat transfer from the surface of the 1 by 1 meter section of the plate. I found this one. Also, determine the overall effectiveness of the fin. So let's calculate overall effectiveness. So if I don't have any fin, the total area with no fin is going to be 1 by 1 meter. Because of the clear reason, if I don't have any fin, the total area is going to be 1 by 1. Okay. Now let's calculate heat transfer rate when we don't have any fin. It is going to be H area with no fin times TB minus T infinity. This is 35 times 100 minus 30, which is going to be 2,450 watt. And now fin effectiveness is going to be Q dot when we have fin and Q dot when we don't have any fin. So when we had fin, it was 17 kilowatt, 17.4 or 17,400 watt divided by 2450 watt, which is going to be 7.1. And this is our fin effectiveness. Let's have all the solution in one. Or maybe not. I'm going to post this solution later on the LearnJSU. Okay, thank you very much, and see you next time.